We have a connected particles question, pulleys, but here the difference is that there are two particles connected on the right-hand side. Don't normally get that. Let's read things through, and as I go, I'm going to add some forces onto this diagram. So here I've got 0.6 g, the weight of P, and then the forces acting on Q, it's going to have its own weight pulling it down. They're attached to the ends of a string, so there's going to be some tension. I'll add the tension in a minute. We've also got a rough horizontal surface. B is held at rest on the surface 2 meters from the pulley, and Q hangs vertically below the pulley, and it's attached to a third ball R of mass m kilograms. So this is going to experience its weight of mg. And then R hangs vertically below Q. Okay, good. So the system is released from rest with the strings taut. Ball P moves towards the pulley with acceleration 3.5 meters per second squared. So I'm going to use a double arrow like that, and a constant frictional force of magnitude 4.5 newtons opposes the motion. There's also going to be a normal reaction, which in this case will be exactly the same as 0.6 g. And it's not really essential to play around with those because friction's already been given for us, whereas like at some point in second year, you'd start using the normal reaction to help calculate friction. There's going to be one other force on P, and that is the tension to the right, because at the end of the day, it's being pulled to the right. There's got to be something pulling it. So I'm going to call this T1, because it's actually more than one tension. And then there'll be, if we look at Q, what stops it just falling under free fall? It's the tension of the string above that's keeping it up. This is going to act up, and this is going to be T1. So those are all the forces on P, the ones in blue. And then I've got these forces on Q in red, but actually there's going to be another one because there's something that's holding R from just falling under free fall. That's going to be a second tension, and we can't say it's necessarily the same, so I'm going to call it T2. And then it's this that Q then experiences itself acting down. Okay, it doesn't quite know what's underneath it. You can't just say that it's mg acting on it. Instead, it's going to be T2 acting down. So that is our setup. The only thing I've not included is that because R is accelerating to the right at 3.5, then Q and R are both also going to be accelerating down at 3.5 meters per second squared. So I could add them on. All right, we're all set up. So considering the motion of P, find the tension in the string connecting P and Q. That's going to be the T1 that we're interested in. So I can focus on P, apply F equals ma to the right. So T1 minus 4.5 is going to equal 0.6, that's my m, times the 3.5 that I have from before. There's enough information there to be able to work out T1. So 0.6 times 3.5, and then I'm going to be adding 4.5. This gives us 6.6. 6.6 newtons. I just write it like that. Hence determine the value of m. Give your answer correct to three significant figures. Now there's two approaches to this. You could deal with Q and R separately, construct a system of equations and solve them. And I will show you that way. But it's actually going to be quicker to consider Q and R together, basically as a single particle. Because now, let's just draw them as like a block. So their weight is going to be 0.4 g plus mg, which actually I can factorize out in a minute. And then the only thing holding them up is that T1. I don't need to include T2 because now I'm considering them as a single thing. And so if I apply F equals ma down, then I've got 0.4 plus m times g, that's the weight, minus my tension of 6.6. That's going to equal the mass, 0.4 plus m, times A, which remember is 3.5. So that's meant to be a times. What we can do actually is like imagine you had xg minus 6.6 equals 3.5x. Maybe I should write it now as 9.8. So 9.8x. All I need to do is do 9.8 minus 3.5. To be fair, don't really need a calculator for that, but anyway, 6.3. So I'm going to get 6.3x equals 6.6. Now, why am I bringing in x? Because I'm just trying to say it's exactly the same here. It's just x is my 0.4 plus m. So I'm actually going to get 6.3 lots of 0.4 plus m is equal to 6.6. I've just done 9.8 lots of 0.4 plus m minus 3.5 lots of 0.4 plus m. So I get 6.3 lots of 0.4 plus m. I don't need to expand all the brackets and overcomplicate it. I'm still not going to expand the brackets. I'm now going to do 6.6 divided by 6.3, which gives me 1 over 1 and 1 over 21, or 22 over 21. I'll keep it exact for the minute. So then I just need to minus 0.4. And we get 68 over 105. Of course, this is a model. We shouldn't leave our answer exact. Let's write it to three significant figures, 0.648. Okay, nice. Let me just show you another way we could have done that question. So this is like B method 2. And it comes back to treating them separately. So I can look at Q, apply F equals ma down, and I'm going to get 0.4g plus T2 minus T1, which remember was 6.6, equals M, which is 0.4A, or A was 3.5. I can tidy that up a little bit. I'll just leave it for the moment there, I think. So, and then I've got, it was R, also apply F equals MA down. Then it's going to be mg minus T2 equal this time to 3.5 m. And I can add these two equations together to cancel out the T2. See, that T2 is a bit awkward. I've developed simultaneous equations. See, I avoided that when I did it using my first method. So I'm going to get 0.4g plus mg minus 6.6. That's on the left-hand side. And that's going to equal 3.5 lots of m plus 0.4. Now, actually, this is identical to what we had here, so I don't need to finish this off. It would be the same process now to work out m. But it's just I'm just trying to demonstrate how you could use you could treat them separately to do the problem if you wanted. Actually, the answers do it like this, but I would say considering them together is a much better idea. I hope that makes sense also with all the forces. I just want to explain again, just in case you're not happy with it. So I'm applying Newton's third law in lots of different cases here. Every action has an equal and opposite reaction. So because there's a tension, actually I'm not applying it in lots of places because I think like the pulley would also experience a force. That's the kind of the equal and opposite reaction that's going on. But anyway, the main one is the T2s because there's a tension keeping R from falling, it's pulling it up, there must be a tension on Q acting down. That's our equal and opposite reaction. So I hope this diagram is making sense. When the balls have been in motion for 0.4 seconds, the string connecting Q and R breaks. Show that according to the model, P does not reach the pulley. There's quite a lot to unpack here, and I'm going to talk you through it. So we first need to look at the first 0.4 seconds, because in this period, P is going to be accelerating to the right and Q and R accelerating down. But let's apply that on P because we want to know how fast it's moving at 0.4 seconds and how far it's traveled actually. So remember, it starts from rest. It's accelerating at 3.5 meters per second. It's accelerating for 0.4 seconds before the string breaks. So I can do V equals U plus AT. That's just 0 plus 3.5 times 0.4. That actually becomes 1.4. And then S equals UT plus a half AT squared. So it's just going to be a half times 3.5 times 0.4 squared, which ends up being 0.28. So these are going to be pretty crucial, how fast it's going as the string breaks and how far it's moved along. Because now we move to this system where R is essentially gone. Okay, maybe it's falling down, but we're not interested in it because we're focusing on P. So let's look at the forces. We're going to have a new tension acting to the right. I can't say it's the same, so I'm going to call it T3. This is going to be the same friction going to the left, or at least that is what we're assuming. And then on Q, there's going to be that same tension acting up, and then the weight acting down. And let's see what's happening. It's probably going to be slowing down. You wouldn't expect, because if it doesn't slow down, it is going to reach the pulley. And actually, we can show this. P will be slowing down since 4.5 is greater than 0.4 G. Okay, this force is bigger than this force, so it's gonna win. What we should say is eventually when the P stops, it's not going to start accelerating to the left. It's just going to stop. Friction just opposes motion. It's never going to actually cause something to just move along a table when it wasn't already. So it's just going to cause it to stop, and then the friction will actually well, it won't go to zero, but it will just reduce to whatever it needs to be to keep the system in equilibrium. Okay, so if I look at P and I apply F equals ma, because it's going to be accelerating to the left now, let's apply F equals ma to the left. So 4.5 minus T3 is equal to 0.6a. Sorry, I should have done these. I always like to do them in different colors just to highlight they are forces on different particles. So let's go with that. And then for Q, apply F equals ma up. T3 minus 0.4 G is going to equal 0.4a. And I can add these two together. The T3's cancel, and I'm left with 4.5 minus 0.4 G is equal to a. We've got 0.58 as our acceleration. Okay, so now we can apply that on P. Let's apply it in to the right. And this is 0.4 seconds to when P stops. We're going to find out how far it's traveled for when it stops and show that that is going to be less than 2 meters overall. Remember, we've also got this 0.28. So U is going to be 1.4. My initial velocity in the second phase of Suvat is the final velocity from the first phase. Okay, the string breaks, it's going at 1.4 at the end of it. It's still going to be going at 1.4 at the start of the second phase with this new acceleration. A is going to be minus 0.58 if I'm applying Suvat to the right, and V is going to be 0. So I can do V squared equals U squared plus 2AS, ignore the time. 0 is equal to 1.4 squared minus 2 times 0.58 s, and that means s is going to be 1.4 squared divided by 2 times 0.58. We get 1.6896. So the overall distance moved by P is going to be the 0.28 we had before plus 1.6896. So it gets very close to the pulley, but doesn't quite reach it. 1.97 meters. We could say 1.97 is less than 2, so P does not reach the pulley. Hey, that's a challenging question on this topic. The fact that we've got, actually it doesn't really matter because R is gone, but you do have to do the earlier parts to be able to get the acceleration, I think, and then getting rid of it. But this time, it's like normally when you cut it, you then have nothing there, but actually we've still got Q there trying to cause P to move to the right. It's just there's a frictional force that stops it. So yeah, really interesting take, and I hope all of this makes sense. There's a lot to think about. Two different diagrams apply Suvat in the first for 0.4 seconds to work out V and S, and then consider a whole new diagram with a different acceleration, different tension, work out the acceleration, put it into Suvat, work out how far P has gone until it stops. Okay, we've got one last part to this question. So it's given that in fact P does reach the pulley. What factor in the modeling could account for the difference? So what have we assumed in our model that maybe we shouldn't have assumed that would have caused, like P would have actually have reached the pulley? So I went with the weight of the string. I just thought, you know what, if the string's really heavy, then maybe Q will be a little bit heavier and it will cause P to get there. And that was accepted, so that was good. I'm just going to show you the other options you could have gone with. So this is what the answers go with. They say both P and the pulley are modeled as having negligible size. They go with dimensions instead, rather than objects with dimensions, and therefore this could account for why it reaches the pulley. We've gone for that as their main answer. Other accepted answers that the friction may not be constant. See, the string not light, so it's going to have a weight. It's not inextensible. It may be elastic, anything to do with elasticity, extensible. These are all sort of saying the same thing, really. Friction, all that was allowed. What you can't say is you can't just throw out that word air resistance. Quite often it's just it's a good one to try, but here actually air resistance would slow it down sooner. And it's not accounted for if you say frictional force on the pulley part, because again that would actually slow it down faster. Particle smooth and the surface being smooth. Okay, good.